Okay, so in this lecture we're going to talk about tangent plane approximations and differentials. So this generalizes our tangent line approximations and differentials of one variable that we've seen before. So let's just quickly review our tangent line approximations, just so we have fresh in our memory what these are doing, so we can see how this is a generalization. So the idea here is if I have a function of one variable, so suppose this is my function of one variable, and I happen to have some point A where I know f of A and I know f prime of A, I can draw the tangent line here. And let's call this y equals L of x for the linearization. And then recall if I pick some other point nearby to A, so this is say, let's say A plus delta x maybe, or we could call this B even, that if we go up here, we probably don't know what f of B is, but we know what L of B is. So we can say L of B is approximately the same thing as f of B. And the L of B we can actually evaluate. So if you recall, our tangent line is given by this formula. So to get that linearization, we solved this for y. And that gave us our tangent line approximation. So what we saw in the flipped class video is we could do the same thing for this with tangent planes when we have functions of more than one variable. So this is a little bit more difficult to draw, but we'll do our best here. You should definitely look at the flipped class video for a better graphic for how this works. But the idea is pretty much the same thing, is that if I have some surface here now, actually let's make this a little bit more curved so it shows up a little bit better what we're doing. So let's make this a really curved surface. So say this is z is equal to f of xy, and then I can pick some point, say here, so this is say x0, y0 now, and we'll go up and this will be at some point, this is the height f of x0, y0, and then we can draw our plane there. So this is the tangent plane at this point. And if I pick some other value nearby, so let's say I have some point over here, let's just call this xy for our purposes. We'd have some height f of xy here, but we can approximate that by where it is on the plane. So if this plane is given by z is equal to L of xy, then this would be L of xy here, and that gives our approximation. So same type of idea. And so what we saw in that flipped class video is our tangent plane here, which we could write as L of xy, or if we want to just write it as z again, this is f of x0, y0 plus the partial derivative of f at x0, y0, x minus x0, plus the partial derivative with respect to y at x0, y0, y minus y0. So you see it looks very similar to our tangent line approximation above. We just have more variables now, so we have the two different derivatives coming in, the partial derivatives there, to give us our tangent plane approximation. So let's go ahead and try an example with this. Okay, so we want to find the tangent plane approximation, which we can also sometimes refer to as the local linearization, because it's turning a general function into something that looks like a plane, of the function f of xy equals x squared y at the point 3, 1. So there's a few things we need for this. First, we need the value of the function at that point. So this will be 3 squared times 1, which is 9. We need the partial derivative with respect to x. So that's going to be 2 times xy. And then we need to evaluate this at 3, 1. So this is 2 times 3 times 1. So this is 6. I need the partial with respect to y. That's just x squared. So this is 9. And now we have everything we need for this tangent plane approximation. So this is the value of the function at the point plus the partial derivative x minus 3 plus the partial derivative y minus 1. So pretty straightforward to actually find the tangent plane approximation. As long as you know how to take the partial derivatives, there's nothing difficult about that. So let's see some examples where we use this idea in word problems. Okay, so van der Waals equation relates the pressure P and the volume V of a fixed quantity of gas held at a temperature T. We're going to say A, B, N, and R are constants here, and van der Waals equation is given by this equation here. So a few things we're going to want to do with this. So the first one is let's express P as a function of T and V. So that's our first step. So we want to isolate P in this equation, so let's start by dividing both sides by the V minus NB. And then we can subtract the remaining term to get this. Okay, so now for our second thing we'd like to do with this, let's write a linear, let's say tangent plane approximation maybe. Okay, and so we want to write a tangent plane approximation for how the pressure changes, so delta P, which is going to be P minus P0, resulting from a change in temperature and a change in volume. So the first thing we want to do is we want to look at these partial derivatives. So we want delta p, delta t. Let's start with that. So notice when we're looking at the equation above for p, there's only the t is only to the first power in the first term. So when I take that partial derivative, I'll just have nr over v minus nb. And that's it. So if I want this at a particular point that we know, so say this is t0, v0, this is just nr over v0 minus nb. And then we can do the same thing for with respect to v. It's just a little bit more complicated now. So notice for the first term, we're going to have to use chain rule. So I'll have nrt, and then when I take that chain rule, I'll have a minus 1, and then I'll have v minus nb squared. And then for the second term, I have the v's to the minus 2, so I'm going to have minus, and I'll have minus 2, and then n squared a over v cubed. So this becomes 2n squared a over v cubed minus nrt over v minus nb squared. And then if I want this at a particular value, t0, v0, this just becomes 2n squared a over v0 cubed minus nr t0 over v0 minus nb squared. And so when we write our tangent plane approximation, this is going to be, the pressure here is approximately our tangent plane, which is L of TV, and this is P T0 V0 plus delta P delta T T0 V0 T minus T0 plus delta P delta V T0 V0 V minus V0. And so what I can do now is I can take this term and bring it to the other side. And so I have that delta P that I'm interested in, which is P of TV minus P of T0 V0. And this is approximately delta P delta T T0 V0. And I can rewrite this as my delta T. And now I just need to fill in those terms that I found. So delta P is approximately, well, I had nr over v0 minus nb delta t plus, and then I fill in this other term, the 2n squared a over v0 cubed minus nr t0 over v0 minus nb squared delta v. And that gives us our approximation. Now we can also see this in terms of differentials, instead of just thinking of this in terms of the tangent plane. So if we recall from the flipped class video that if I have z is equal to f of xy, then dz is f sub x at x0, y0 dx plus f sub y of x0, y0 dy. And this is approximately delta z. So if we want to think of this in terms of a picture again, do our best to draw a picture of this. So I have my surface here like this. If I know some value here, so this is, say this value here I know, so this is f of, say, I don't know why all of a sudden we're doing this. So this is the value we know, and then the value we're interested in, say, is here, is say f of xy. Then the distance between these two is delta z, that's the exact value. And then if I were to draw the tangent plane here, the difference between this and whatever this value up in the tangent plane is, so that distance is dz. So again, the flipped class video has a better picture of this to look at, but it's a similar idea to the differentials in the one variable case. So delta z is the exact change in z, and dz is the approximate change. And so this ends up being L of xy minus f of x0, y0. And that's how we get this formula up here for the differential. So let's look at an example for this. Okay, so we use differentials to estimate this. Of course, we could do this with the tangent plane as well. So first thing I need is the partial derivative. So this is going to be a 1/2, and I'm going to have x squared plus y cubed to the minus 1/2, and then the derivative of what's inside, which is 2x. So this becomes x over x squared plus y cubed to the 1/2. And now I want to evaluate this at my point 1, 2. So this gives me 1 over 1 squared plus 2 cubed to the 1/2. So this is 1 over 9 to the 1/2. So this is 1/3. And then we take the partial with respect to y. So this becomes 3/2 y squared over x squared plus y cubed to the 1/2. And now I evaluate that at 1, 2, and I have 3/2, and then I have a 4 on top, and then a 3 in the bottom. So this just becomes 2. So that means my df, which we got, or dz, either way, this is 1/3 dx plus 2 dy. So in particular then, f of 1.04, 1.98 minus f of 1, 2, this is exactly delta f, which is approximately df. So that tells me f of 1.04, 1.98 is approximately f of 1, 2 plus df. So this is square root of 1 squared plus 2 cubed plus 1/3 delta x plus 2 delta y. This first term there is 3, and I have plus 1/3, and then my delta x is going to be 1.04 minus 1 plus 2, and then I've got, so this is the plus 2, and then I plug in the 1.98 minus 2. And so then we can fill this in. This is 3, and then I get plus 0.04 over 3 minus 2 times 0.02. And that gives me my approximation. Again, if we think about what we've done here, really, this thing here, this is just the tangent plane. approximation. So in reality, the differentials in the tangent plane we saw above, this example we did with the pressure here, this is really a problem about, might most easily be recognized as a problem about differentials because we're looking at delta P. And we can see this is what we end up with when we get delta P. That's exactly the differential. But we did that problem using tangent planes. And here, this one's more of a problem about tangent planes, but we did it with differentials. So you can go either way, whichever one you're more comfortable with. You can solve the problems either way. It might be good to go back and go through each of those examples and do them with the other method. So the one we did with tangent plane, do it with differentials, and the one we did with differentials, do it with tangent planes, and make sure you see how you can do it both ways. Okay, so the coefficient of thermal expansion, which we're going to denote as beta, of a liquid relates the change in volume in meters cubed of a fixed quantity of liquid to an increase in its temperature in degrees Celsius, and this is given by dV is equal to beta times V times dt. Okay, so let's let rho be the density in kilograms per meter cubed of water. Okay, so we're going to let rho be our density. Kilograms per meter cubed of water is a function of the temperature. We recall that their density is given by the mass divided by the volume. So let's start by writing an expression for d rho in terms of rho and dt. So that's our first step. So notice that we have, since rho, thinking of this as a function of v, is m over v, delta rho delta v is minus m over v squared. So if we think about what this is, d rho, in terms of our differentials, this is delta rho delta v at v0 dv. So this is just a differential from a one variable case. But now we want to use what we have above. So first let's fill this in with what our d rho is. This is minus m over v0 squared dv. And now we can use this formula above for the dv. So this is minus m over v0 squared. And now remember this is beta v0 dt. And so this is minus m beta over v0 dt. And so that m over v becomes rho dt. So that gives us our d rho in terms of beta, rho, and dt. So that's our first step. Now let's actually do something with this. Okay, so I'm going to draw a graph here that's going to give the density of water as a function of the temperature, and we're going to use it to estimate beta when the temperature is 20 degrees Celsius. So let me give this graph now. So this is T degrees Celsius. This is rho kilograms per meter cubed. So let's 20, 100 is out here. Let's draw a graph here. So we're going to say this goes out like this and curves way over here like this. Okay. Okay, so what we can do then is we can say, okay, well, let's do our estimate here when now I drew this a little bit funky. Let me redo this graph real quick. I want it to start at 1,000, not start above 1,000. Something like this. And so when I go up, I can estimate this. Be right about there. So let's estimate when t equals 20, we'll estimate rho is about 997 kilograms per meter cubed. And now from part A, right, we had this formula here for d rho in terms of beta and dt. So if we solve that for beta, we can say this is a negative d rho over rho dt. And so we can look at our points here. So we have 2 points. I have 0, 1,000. That's why I wanted the graph to go through 1,000. And then the point 20, 997. So for our point, dt is equal to 20 minus 0, so 20. And d rho is 997 minus 1,000, so negative 3. So that would tell me my beta is approximately negative 3 over 20 for the maybe I should write it in the other order. So the rho here is 997 and then the dt is 20. And so if you were to evaluate this with a calculator, we get about this for our estimation. Okay, let's try one more example to see one more way we can use differentials in this setting. Okay, so we have a closed rectangular box. We measure the sides as 80 centimeters, 60 centimeters, and 50 centimeters, and each one of them might have an error of up to 0.2 centimeters. So this should, if you go back and look at how differentials are used with one variable, this should look familiar. We just have more variables now. So let's use differentials to estimate the max error in calculating the surface area of the box using these measurements. Okay, so let's think of what our box is here. It's just something like this. We can call this x, y, and z. So my surface area here of x, y, and z is 2 times xy plus 2 times xz plus 2 times yz. And now this is a little different because we have more variables. So we couldn't draw the differentials out so with 3 variables, but the formula is going to be the same idea. So my differential here is s sub x dx plus s sub y dy plus s sub z dz. So s sub x is going to be 2y plus 2z. S sub y is 2x plus 2z, and s sub z is 2x plus 2y. So we can fill that in for our differential, and this is going to be 2y plus 2z dx plus 2x plus 2z dy plus 2x plus 2y dz. And now we can call these whatever we want in terms of our numbers. So let's say x was the 80, y was the 60, and z was the 50. And now our error for each one was 0.2 centimeters. So delta S, this is the error in surface area, because think of this as the difference between the measured value and the actual value. So delta S, the error of this, is approximately this, which is, well, we can say 2 times 60 plus 2 times 50 dx plus, let's say less than or equal to this, plus 2 times 80 plus 2 times 50 dy plus 2 times 80 plus 2 times 60 dz. And so this is 220 absolute value of dx plus 260 absolute value of dy plus 280 absolute value of dz. And we know these errors are all bounded by 0.2. And so this comes out to 105.2 centimeters squared.